All right, let's get started. So yesterday we jumped around in the July 9th lecture and the July 10th lecture for the sake of being able to talk about input redirection as early as we could. So now in this class we're going to do the rest of those other lectures, which have information that's still important, will be on the test probably, but less urgently needed information. And since this lecture starts off with questions, I figure I'll ask again. Assignments due in a couple days, so any new questions about it since yesterday? None so far. We'll see if that's a good thing or a bad thing. I've also been getting some really good questions over email. I'll just give you all like 20-ish seconds to think about questions if needed. All right. Hopefully you all know what's going on then. So let's see where we were at. Yesterday, we skipped ahead to writing code that takes advantage of its environment through redirecting standard input and output. That let us use files for input and output, particularly using a file as input in question 2 of assignment 1, without rewriting our code from what was made to use keyboard input. We also talked about the memory layout of a typical program. And of course, we used fgets alongside that last learning outcome. So today we're going to be looking further into memory layouts. And that'll be mostly through taking our string example. So get your strings.c ready. We're going to take that example and basically just mess it up. We're going to be doing a lot of very terrible things that you shouldn't do in real programs. But for the purposes of this class, it's fun, and you should definitely know what not to do and how what not to do works, so you can avoid doing it accidentally. Yeah, we did that. We did that too. So we're going to be talking about the stack. And yeah, this is the good part. So I'll give you all a refresher on stack frames. We'll probably be switching back and forth between the document camera and my screen throughout the lectures. So reminder again to anyone watching this on the recording that all the drawings will be available on UMLearn separately from this lecture, but they won't show up on the recording because they're not on my computer. So, memory layout of a typical program has the code section, the heap, and the stack. Whenever you call a function, it adds a stack frame to the stack representing that function. So there will always be a main stack frame to start because your program starts at the main function. And then say your main function is for a string program and it calls a function string length. So that function's frame would be added onto the stack. And I think our custom string length function that we talked about when writing that example didn't actually call any more functions, so the stack would stop growing there. But for the sake of this explanation, let's say we, didn't know about array indexing. We don't, for writing this string length function, we're also effectively ignoring strlen. But anyway, let's say we didn't know that strings in C are just dumb arrays of char, and we wanted to call some sort of char at function. That would be added to the stack too. And as the functions exit, their frames are popped off the stack. I'm just going to turn my mic volume down a bit to hopefully avoid that screeching. So this is all a part of the stack. And within each stack frame, there are several parts to it, such as, well, basically just local variables and pointers to stuff that's useful. So I'm just going to get out my previous example so I could refer to it. And then I'm going to ignore it because we're actually just talking about a generic main function. So we'll just say it has a local variable, another local variable, and an array with 3 entire elements. This is all just review from last class. And then it has a return address and pointers to things that I'm not allowed to call objects, such as stdin and stdout. So if you learned about stacks in Comp 2140, that is exactly what's going on your computer as you call functions. And we're going to use that knowledge for evil. Because our copy string function uses these confusing things called output parameters, and what the heck, parameters are input. I just want to return an array of char or string or whatever you call it. So let's attempt to do that. I'm going to do some code first and then take that step back. Well, I'm already SSH'd. I'm going to log out and back in again for the sake of people following along. I should probably remove my SSH key, so then I'll have to put in my password each time, and then that'll slow me down a bit more, which will be useful for you guys. Whatever. You've done this hopefully many times before. We're going to change directory into our Comp 2160 folder. And I want to use our string example from last class as a base, but I don't want to overwrite that directory. So I'm going to use cp copy instead of makedir. This won't work. Oh no. CP, or that That command might look like it works intuitively, but remember, these commands generally look for paths to files, and to make them work on folders instead, we need to give it the -r argument for recursive. Okay. Now we're back to that program that we wrote last time. We are naive and unaware of the pitfalls of the stack, and we think that having copy string return void and take its target as a parameter is dumb, so we're going to change that. Attempt 1, we do this. And also remove this. Going to do DW to delete word, and then pressing period will repeat my last action. Period, period. Easy. And because that was just our forward declaration, I also have to copy this change to its implementation. But I'm going to try and compile it right now anyway to show off the error message. Clang, wall, strings.c, output, strings. Uh-oh. We didn't even get to the point where it can complain about the interface differing from the implementation. This syntax, which probably would have worked with Java, doesn't work. Brackets are not allowed here. Place the brackets after the identifier. That's consistent with how we have to define arrays as local variables. So let's try this again. Attempt 1.5. Oops. I press capital A to insert, or to enter insert mode at the end of the line. So will this work? Spoiler alert, no, but this entire example is dedicated to showing off what not to do in increasingly bad ways, but thankfully increasingly applicable ways. This, what we're looking at right now, is just stupid. Some stuff that we'll look at later in this lecture is stuff that you might be led to do accidentally. Okay, so we have fixed that syntax error about brackets, but we're still getting function cannot return array type char brackets. Oh well, I guess we can't return arrays, except we know from previous lessons that arrays are just memory addresses, which are just pointers, and we can use pointers oftentimes interchangeably with arrays. So let's try and make copy string return not a char array, but a char pointer. These are equivalent in functionality, but maybe the compiler will understand what we're doing. So the syntax for a pointer is to have the type that the pointer is pointing to, followed by an asterisk. With this one character, we went from having copy string. Oh wait, I'm just going to remove those ugly brackets before I forget. Now, with that single asterisk, we changed the function from one that returns a char, so a letter, to a char pointer, which is the memory address at which a char is stored. And then, since pointers and arrays are exactly the same thing, we can then use array indexing on that pointer to access values that are next to it and treat it as an array. Okay, we got better errors. That's probably the best news you could get while programming. It's no longer concerned about us returning an array because we're allowed to return pointers. It may seem strange that I keep saying arrays and pointers are equivalent, and yet I can return a pointer but not an array. But I don't know, we'll see why later. What are our errors now? They all have to do with just having the interface different from its implementation, as well as its usage. So these are pretty easy errors to fix. Let's do that right now. So one of them is that when we called copyString, it had too many arguments. That's natural because we had 3 parameters and we changed it to 2. So let's fix that. I don't know where we call copy strings in this program, so I'm going to search with / copy string, and it's right there. So I'm changing the use of other name from a parameter to the return value to reflect the changes that we made earlier. And doing the same here. And since we no longer have target for ourselves, we need to define it here ourselves. This should work. We might return to this. Speaking of return, we can just return target. So let's see if that works. Woohoo! These warnings are going to keep getting worse and worse, but our errors, those are all solvable. So let's see what we got. Array type char12 is not assignable. We can fix that pretty easily. Okay, let's fix the first one. What happened here is a difference between arrays and pointers that's much easier to explain. The error we were given is that the array type is not assignable. So we're going to fix that by using a pointer instead. It's kind of weird that arrays are not assignable, but pointers are. But I think that was a limitation deliberately inserted into the language based on the conceptual model of what an array should be. Assigning a value to an array might imply that you're setting each index or setting each value inside of an array to certain values. But remember, arrays are just memory addresses. So when you assign something to an array, you're just assigning it a new memory address. So that's my theory on why it's not assignable. In any case, we're just going to change the syntax here. And we'll probably still get these warnings, but not the error. Woohoo! I'm a bit nervous about those first 3 warnings. I was goofing off with this before class and verified that everything works, but I'm not quite sure how to handle these. Luckily, I have a working, doesn't work, but it doesn't work in the intended way in which it's supposed to not work. So if these warnings end up giving us trouble, I'll be able to save ourselves. So let's try running it, because it sure did compile. Okay, we can already start to see some jankiness. I'm pretty sure we didn't just create a string that's just Z. And that probably has to do with these warnings. I'm going to check the implementation of copy strings in my other program, just to make sure that we don't go into some unrelated rabbit hole that's unrelated to the rabbit hole we're supposed to be going into. Oh, I defined target differently. That must have been the source of the errors. Oh, of course. I still have the array syntax. I accidentally doubled up the array syntax and the pointer syntax, so this line 88 actually defines an array of char pointers. Every element of the array is the memory address to where you'd find another char. That's not what we want. Let's just use an array, and hopefully we should be back on the right track. Okay, we got only the warning we were hoping to see. And let's see how the function, or how the program works. Okay, string copy works again. I think that when it was not working correctly, this loop was assigning to target the elements of source, which are just chars, which are equivalent to small int values. And then the output was treating those as pointers. And I'm kind of surprised it didn't segfault, but I guess the value at the address that is equal to the integer value of the characters of source. Sorry, that was like 6 layers of indirection. Hope you're able to keep up. I'll try to say sentences with fewer ofs in them in the future. But I think that the memory addresses that we inadvertently pointed to may have held the value 0, causing the target string to have an early end of string character. Neat, but not too relevant. So that warning we're getting, address of stack memory associated with local variable target returned. Let's switch back over to the document camera. And also recall that our program seems to work right now still. It's working Hello? Oh, guess the battery ran out. Our program is working, but for bad reasons. Our copy string function has a stack frame, much like those. I'm just going to label this review. And now copy string. Well, it just has one local variable, target. And notice that this variable, or this array is variable length. The amount of memory that's allocated here varies based on the length parameter given to it. That might sound pretty trivial coming from Java, but it's actually a pretty recent, or I shouldn't say recent, C gets updated like every decade or so. It's a relatively newfangled feature by C standards. So, copy string. It has the variable target. And of course, more values for however long target is. Up to index length -1. Then it has its return address. The memory address of the code that it's supposed to return to, in our case, the location in which it was called in the main function. And then it probably has these pointers, but who cares? We want to think about stack frames here. So we started with main, and we called copy string. We returned the array target, which, as you may know, is just a memory address. And just illustrating this to show that this is all contained in that. The memory address target is inside this stack frame. Once copy string returns, that memory is all deallocated. It can be used for whatever the program or the operating system wants to. So what would happen if we called more functions? Where's my eraser? There's my eraser. Copy string, its memory is deallocated, and then, I don't know, let's say we called string length afterwards. It would get its own stack frame, reusing the addresses used by copy string, but that pointer to char, aka char array, that it returned, still points to the memory that was once occupied by copy string stack frame, but now it points to somewhere within string length's stack frame because that memory was reused. So as soon as string length, or whatever function we use, occupies or uses that memory in its stack frame, that pointer to target will be worthless. It'll point to whatever string length happens to be storing. So let's see that in action. Not actually going to use string length, have a bit of a canned example, but you'll see what's up soon. So let's keep all that code that we wrote last time and start writing stuff here. I have two parts of the example I could do, and I'm deciding which one I should do first. Okay, the second thing is more exciting, so let's do the less exciting thing first. I'm going to define a few pointers, so a few strings. Hopefully you've seen similar syntax before. Like if I didn't have this asterisk, this would just define or declare 3 char variables. Pretty easy. And this part of the example illustrates a common syntax pitfall that, well, happened to me. It will happen to many of you, but I want to warn you about it. You would think that char asterisk string 1, string 2, string 3 will define 3 char pointers, but actually string 1 will be a char pointer, and string 2 and string 3 will be just regular old chars. I really don't like this about C's syntax. It's much more intuitive to have char star represent the idea of this type being char pointer. But unfortunately, it doesn't work that way. We're declaring variables of type char and then specifying that each one is a pointer. Like that. So when you're defining individual pointers, doing it like this with the array next to the, or the star next to the type is fine. Defining it this way with the star next to the name is also fine. They are equivalent in functionality because you're only declaring one pointer. The choice is up to you. This is more intuitive as to what other name is, but this is more consistent with the syntax you'll have to use when defining multiple pointers. Which one you use is up to you. I'm just going to be consistent with what I've already written and write the pointer like this, but I think in general I would recommend putting the star next to the name. So we're going to copy some values into these strings using our copy string function, which seems to work for our program so far, but clearly has something wrong with it. And then we'll make it go wrong. So I'm going to write a printing line that I'm going to repeat a few times. String 1 is this. String 2 is that. And string 3 is that. we're going to assign values to these three strings and repeatedly check up on all of these. So what did these look like initially? Well, I didn't give an initial value for any of them, so technically I have absolutely no clue what they're going to be. That is undefined behavior when you have a variable that is not initialized. So what's about to happen is completely up to whoever implemented the C language writing the compiler. Woohoo! Yep, we're getting a bunch of warnings for not initializing variables. The compiler is just begging us to stop this example, but you guys need to know about stack corruption. They're all null. Our compiler author was nice to us, and this is a pretty intuitive result that a pointer that we didn't tell to point to anything points to nothing. And I'm just going to put a new line in front of this output just to make the whole thing prettier later. So now we're going to assign a value to string 1. So let's copy our name. And I think copy string also takes the length of the string. And in a real program, you should totally use strlen. But for the sake of this example, we made our own function string length. So we're going to use that. And then copy this with Y to yank, and then P to paste. Accidentally copied that other assignment as well, so I'm going to DD to delete that line. Oops. Unmatched brackets, classic. So that was on line 47. So once I open Vim, I'm going to type colon 47 to get to that line. Capital A to insert at the end of the line and insert that bracket. Now it's back to yelling at us about uninitialized variables. Excellent. Okay. We successfully copied my name to string 1. Good stuff so far. Now what happens when we assign something to string 2? I would use other name, but we already copied name into it, so let's just use a string literal. Some other name. Oh, wait. We're not done yet. I'm just going to do colon W to write. And then I'm going to copy and paste that printf line. What? Did I do unmatched brackets again? Dang. I didn't note the line number, so we're just going to scroll to it manually. There we go. String 1 and string 2 are both some other name, even though we clearly just assigned those variables unique values. we use copy string twice with completely unique strings. This should never happen. Well, it did happen because the value that we assigned to string 1 points right here, and then we called copy string again. String 1 still points right here. So calling copy string again resulted in a specific variety of stack corruption in which one instance of the function overwrote the return value for the other instance of the function. I guess I only needed 2 strings for this example. String 3 will remain null, I guess. So we saw how attempting to return an array that's stored on the stack can lead to corruption when calling the same function multiple times. Now let's call a different function. We're going to make a contrived example of a function that's designed to corrupt the stack. But really, this could happen with anything. I'm just going to call it goofy function. If we compiled this right now, we would get an error about it not being defined. So let's just fix that in advance. First, by forward declaring it. And then by defining it. And all this function is going to do is define an array. And to guarantee stack corruption, I'm going to give it a really big value or a really big size. But this will probably still work even if I just have, well, 1. Or no, it probably wouldn't. See, probably will work with 1, but I'm going to use 1,000 to be safe. Remember, all those stacks I've been drawing are just a simplified model of how the computer works. It does a good job of describing it for our purposes, but real operating systems are way more complex than that, and so we don't know exactly what order local variables are stored in. Not done yet. I'm just writing, and then after this call, I'll print my stuff again. Oh, it still seems to work perfectly. Strange. Well, I guess we're going to use the same fallback as before. Let's see the function that I wrote from the comfort of my own office. Office hours coming soon, by the way. And see how it corrupts the stack. Okay, yeah, that's more what I wanted to see. Let's check the code for how it differs. Looks mostly identical, but with different strings. Oh, of course. I initialized that array because I was a slightly better programmer when I wasn't using half my brain power lecturing. I guess this is just more undefined behavior in action. when I declared the array but didn't initialize it, it's up to the compiler authors to decide what the program should do with the memory. And I guess that when I just defined it without initializing the values, it didn't do anything to those values. Big array occupied a certain region of memory. That region of memory may or may not have had stuff that was used previously, and it seems it just didn't bother changing it. So let's go back to the program that I'm writing live and do a slightly better job and initialize the array. So this small modification here will change the functionality of the function from just marking 1,000 memory slots as belonging to Goofy function to marking 1,000 memory slots as belonging to Goofy function and then also writing a 0 to all of them. That's more like it. Since our function initialized a bunch of memory to 0, it overwrote the address that all those strings were pointing to with zeros. And since 0 is a value used by the end of string character or the null byte, these are just empty strings now. So previously we had copy string on the stack. It was pushed when we called it, popped when we returned from it. That happened a couple times. And then we called Goofy function. Which used the exact same memory as copy string, but now instead of that target array that contains or points to a string that's to be returned, it's just a bunch of zeros, baby. Notice as well that Goofy function's stack frame is physically larger than copy string's stack frame because its array is larger. It just needs more stuff to function. This is actually not a concern, which might be kind of surprising because all class we've been talking about things that are going beyond the bounds of where they should be writing. But a stack grows upwards. There's lots of free space above the stack. Or I guess if you're storing it left to right, like on the tape metaphor from earlier, to the right. But whatever direction you choose to think about it with, there's lots of free space that the stack can grow into. Which I guess you can illustrate by this stack frame being taller. I don't know. It just grows further into the allocated space for the stack. I suppose that if you defined a truly humongous array, you would get a stack overflow because the stack would grow beyond all the space allocated for it. But I have no idea what that threshold is, and I'm not going to try and find it. So now I think we can go back into the slides, and this will serve as a sort of recap of all the crimes we just committed. So our first attempt at making copy string simply return a value instead of using an output parameter was to just change its signature to give it a char array, but that didn't work. And we needed to keep in mind that an array is an address, so the location in memory where information starts. Java arrays probably contain a whole bunch of metadata, such as their length. C arrays are just straight up data. So this code block is like what we did in Goofy function, where we made an array of 1,000 elements. Same behavior as 10 elements. So starting at the address R refers to, it gives us space to store 10 integers. And so if R is an address, we want to be able to communicate that address. And along the way, we solved some syntax issues to do with returning an array versus a pointer, and issues that were probably deliberately caused by the C authors due to how arrays work. So if you can't return an array, use a pointer. This I probably should have interweaved with the code example, but it's good to be able to write all that code and then review what we just did. And that would have been the cliffhanger to last lecture, but we spent a little bit of time yesterday looking at some content from the following lecture. So now we're going to finish today's lecture, excluding the stuff that we skipped to yesterday. This is even more confusing indexing than our code. Yep, we're going to keep working on strings.c. So let's see these learning outcomes for this lecture. We've been looking at this for the whole course, mostly by writing unsafe code so you know what not to do. This is a mix of today's content and yesterday's content. We're just dipping our toes into memory management, starting with pointers. And this is what we did yesterday. And that last one is another thing that's ongoing. Woohoo! And that is coming up soon. So let's just talk about pointers some more. A pointer is basically another primitive type. You could think about it that way. We have int, char, float, and pointers to all of those. We declare pointers by putting that asterisk on the variable name. And as we saw, you could put them either next to the name or next to the type. They are equivalent in functionality, but sometimes one is more readable than the other in different situations. So you can't return an array, but you can return a pointer. You could think of this as being how the return address on our stack frame, that's only one slot in memory. So arrays, by definition, take up multiple slots. And so you can't shove that all into the return address. Of course, an array is just a pointer, and you totally can store a pointer in a return address. Oh, sorry, return value. Return address is the location in code it should refer to. I'm just going to add return value to the stack frame. So this is what can store a pointer to the start of the array, but not the entire array. So it says, let's keep working on string copy, but we did just do that. And we got this warning. And we just ignored the warning and paid the price. Don't ignore warnings. Yeah, don't. So what was happening there? The errors that we introduced exploited how the stack works. So when you call a function, as we saw in that drawn example earlier, a new frame's added to the stack that contains enough memory for all of the function's local variables to be stored. The machine executes code inside that function. And then when the function returns, the frame is popped off the stack. And what happens to values in stack frames depends on the platform. The fact that we were even able to access the strings that we defined, like the fact that we were able to get the value of string 1 now that it refers to uninitialized memory, that depends entirely on the platform. And we got sort of lucky that Aviary and the Clang version within it just happens to not zero out stack frames that have been popped off. It's totally reasonable for another C implementation on another platform to pop that stack frame and then set all of these values to 0, or even fill them up with garbage or whatever. There very likely is a C implementation that does that, because you can probably see why zeroing out the memory associated with stack frames that we're done using is a helpful security measure. We could set goofy function to perhaps define a really small array and then access that array out of bounds, and then it would access the data used by previously called functions and maybe steal some information that way. Be a lot of fun. So that's been a little whirlwind tour of the stack, and I hope that showing you all how you could really mess with the stack and cause some, or create some functionality that seems to work at first but is actually horrible. I hope that gives you some illumination on how the stack works. And now, sort of related to this is another input function that you could use in C called scanf. Why is it bad? Well, first we need to know what it is, and then we'll look at an example. Input format conversion. There's a ton of information here, but what we really need, what pretty succinctly explains why scanf is bad, is actually right here. We see a bunch of different versions of scanf, all of which have slightly different parameters, but none of which have an argument for how long the string should be, how much information it should take in. And that can cause another buffer overflow. Woohoo! So there's an example that comes not from this course, but from a blog that wrote an article about security in C and some pitfalls of scanf. You can access this example on the course webpage. I put it alongside the files for this lecture. This isn't required reading. Oh no. That's my reminder to put an ad blocker on the browser I use for lectures, I guess. This isn't required reading, but it's pretty interesting. It details how the stuff we've been talking about with illegal array indices can be used for evil. There's a code example in here. No need to code along, but I will post the example on the course webpage after the lecture's over. For now, you just need to watch. Was it buffer overflow example? Yep. So this is code that you should probably not use in most situations, most of the time, and you should maybe be a little bit cautious too, about it. It's a little password verifier. So take a moment to just read the code. We use scanf to accept a password. We compare it to the correct password, hunter2. And as an aside, strcomp has a pretty weird return value. It returns an integer that has something to do with the lexicographic distance between two words. And you don't need to know what lexicographic distance is, except for the fact that if you compare a word to itself, they will get a lexicographic distance of 0. It's like saying that the distance between your house and your house is 0 kilometers because they're the same place. So if it returns anything other than 0, this Boolean value will evaluate to true, and we follow the code inside the if statement, wrong password. If it's 0, we have the correct password, and we set success to 1, which allows us to get to the super secret hideout. This code looks pretty airtight. It's not as obviously blatantly bad as that previous example, so let's try and run it. No warnings. That's great. This must be a good program. So I know the password. Hunter2. Awesome. Now I'm going to get it wrong. Wrong password. So far, so good. And I already forgot the password. What was it? I think it's one of those super secure auto-generated passwords. I feel like a hacker mashing my keyboard like this. Yeah, that's probably it. Woohoo! So it recognized that the password was wrong, but then gained us access to the super secret hideout anyway, and then crashed. So what the heck happened here? Success is stored right next to password, and when we entered more than 15 characters, we just kept writing beyond the edge of the buffer, and I guess in this specific implementation of C, success is stored to the right of password, which makes me think that maybe the local variables are popped onto stack just like stack frames, but whatever, that's not the point. We wrote a non-zero value to success because one of those chars in my key smash was, well, not the null character, so it wasn't 0. It wrote some non-zero value into the memory location of success. So even though strcomp verified that they are different strings, success was still non-zero, and we still got there. And then at some point we got a segmentation fault. I bet we also overwrote the return address, and then the main function's return statement went not to some operating system routine to free up memory associated with the process, but to whatever garbage we put into password. So yeah, scanf is bad, don't use it. And that's a pretty weird lesson to give if you've never heard of scanf. The real lesson is functions in languages that don't manage memory for you are dangerous if they don't implement any sort of bounds checking. Whenever possible, like absolutely whenever possible, use functions that give you some sort of parameter for the length of the array or string that you're giving them. And this will avoid entire classes of bugs. So I think that's it. Oh yeah, maybe think about this for a little while. Reflect upon it while you're studying. What makes Java safe? What makes C unsafe? It's bounds checking. This looks familiar. We did this yesterday. The takeaway that you absolutely need for question 2 of the assignment is that you can use this less than sign as an operator to redirect a file into standard input. But if you're curious more, watch yesterday's recording. Woo! So we got through all those learning outcomes at the last 2 lectures. We sort of jumped around, and I hope it wasn't too confusing, but as of now, we're like right on schedule for these lectures. So tomorrow, we're going to look at how C source code is compiled to machine code, which will indirectly give you lots of knowledge on how to deal with specific error messages in C and also a bunch of other languages. Like the lessons in the next lesson, what language was it? Maybe C#, don't quote me on it. The point is, the lessons in this next lecture saved my butt during a work term. So if you're in the co-op program, it might save your butt too. And if you get a programming job after university, it'll probably save your butt too. So that's it. Enjoy the next 4 minutes and the rest of the evening. And I'll see you all tomorrow.